In this lesson, we're going to talk about how to solve problems with complex numbers. So first, let's talk about what complex numbers are. And we're going to do that by trying to solve these two equations. We're going to solve quadratic equations using square roots. This first example, I want to show you two options. One of them is just to take the square root. And when we do that, we kind of miss part of the solution set, because if you just take the square root here, chances are you're going to say x equals 4. However, if I solve this using factoring, I'm going to subtract 16, get this equals 0. I can factor this using difference of squares, x plus 4, x minus 4. And when I do so, I see that there are actually two solutions, negative 4 and positive 4. One thing that we tend to do in Algebra 2 when we solve is anytime we take a square root, we can stick a little plus minus sign in the front, and that will cover the fact that we should have two solutions for quadratic equations. Now, this problem on the right is not quite as simple, because if I try to take the square root here, I notice that I have a negative 9, and I can't define the square root of negative 9 using real numbers. So we use what are called imaginary numbers, and this is where their definition came from. It's so that we can take square roots of negative numbers. So when I do that, I'm going to get x equals plus or minus, because I need two solutions. The square root of 9 is 3, but we're going to use an I to denote the fact that it's imaginary. So I is defined as the square root of negative 1 by definition. So let's look more at that. So if I equals the square root of negative 1, then I squared would equal negative 1 itself. Think about if you squared both sides of that. It is important that you have both of these definitions down. So imaginary numbers come when we have negatives on the inside of the square root sign, and complex numbers are written in the form a plus bi, where a is the real part and I is the imaginary part. So you can see in these quick little examples down here, negative 6 plus 4i is an example of a complex number, where negative 6 is real and 4i is imaginary. Same thing here on the second example. Notice the last example, the real part would be 0 because there's no real part written there. There's just a part that has an I. So operations with complex numbers honestly are going to feel a whole lot like operations with binomials. This says, so in these two examples, what is the sum of these two? So remember, sum means to add. And so we're just going to combine like terms, really. We're going to add the real parts together, that's negative 7. And then we can add this imaginary parts together and get plus 2i. And that's all you do. For difference, what is the difference between these two? So remember, difference means to subtract those two. Now, difference is a little bit different, no pun intended. When we do the difference, just like with polynomials, we have to distribute this negative. So this is really 6 plus 8i minus 2 plus 5i. I would encourage you to always rewrite that second part instead of trying to do it in your head. And then again, we'll combine the real and imaginary parts. So this is 4 plus 13i. We can also multiply complex numbers, So remember, when we have parentheses squared, that's something that we will need to write twice. So this is 8 minus 9i, 8 minus 9i. And then we will distribute 64 minus 72i minus 72i. Negative times negative is positive 81, and I times I is going to give me I squared. If you don't understand any of those numbers, pause this video to make sure you see what's happened so far. Now here's a little bit different, something strange here. Notice that this has I squared, but I know my final answer should just have an A and a BI in it. If you remember from a few slides ago, I squared equals negative 1. So really this last part is saying plus 81 times negative 1 or minus 81. So what I do is I think I squared is going to flip this sign every time. So this is really negative 81 right here. Now I have two real parts that I can combine together, 64 and negative 81, which will give me 17, and negative 72i, which is going to give me negative 144i. So there's my complex solution. Let's look at another one of these. On B here, we're going to do the same thing. So 9 plus 6i minus 6i minus 4i squared. So again, this I squared is -1, which is going to flip this to become a plus 4. Combine my real parts, I get 13. Now something interesting happens here. On this one, the imaginary part in the middle cancel each other out. So the answer to this is just 13. Now, this question in itself is kind of important in that something is unique about it from the beginning. If you notice, these two terms are very, very similar, and they are something that we call conjugates. And from this example, we see that when we multiply conjugates, we're going to eliminate the imaginary part. And that is really important to note. All right, so they've got a little proof for you here in the book. And if you wanted to, you could take a second to pause and just kind of view this note and see where that's coming from. But really what I need for you to write down in this moment is to write down these two examples of complex conjugates. So there's 7 minus 8i and 7 plus 8i, -2 plus I and -2 minus I. Those are both examples of conjugates. So this comes in handy when we're trying to divide with complex numbers. So notice that we have this division problem here, 10 minus 2i, and we want to write that in a better form. So we don't want I to be on the bottom, basically, is the issue here. So I'm going to start with 10 divided by 2 minus I, and we just said if we can eliminate I if we multiply by the conjugate. So what we're going to do here is multiply both the top and the bottom times the conjugate, 2 plus I. 2 plus I. On the bottom, so actually on the top, I'll go ahead and multiply that. That's going to give me 20 plus 10i. And on the bottom, remember, I still have to do this double distributing, so I'm actually going to work that out underneath. 4 minus 2i plus 2i minus I squared. Those in the middle will cancel, and this I squared is going to change this. So this is like -1, which is going to become +1. So if I combine, I have 4 plus 1, which means my denominator here is 5. Now I want to split this up so that I can write this a little bit better. This is the same thing as 20 over 5 plus 10i over 5, or simplified, that's going to be 4 plus 2i. All right, something else that complex numbers allow us to do is to factor sum of squares. So if you remember, difference of squares, we've been allowed to factor the whole time. This is something we have to have real numbers for. And if I give you an example, this factors to be x minus 25, oh, not 25, 5, x plus 5, and we end up with 5 and -5 as solutions. Also notice, if you have not ever noticed this before, notice that these right here are conjugates in this example. Okay, that just always happens with difference of squares. All right, and then we can do this other example real quickly. 100x squared minus 9 becomes 10x plus 3, mercy, and 10x minus 3, which is going to give me solutions. Remember, we set these equal to 0, so that's going to give me solutions of -3/10 and +3/10. Also, you should recognize this is happening with that plus and minus, right? Just like we talked about at the beginning. So when we do sum of squares, normally we say this cannot be factored, which using real numbers, these examples right here cannot factor with real numbers. Cannot with real. But they can with complex numbers. So let me show you what that looks like. If I were to solve this and move the 25 over, this would become x squared equals -25, which I know that negative, when I take the square root, will give me an I. So what I can do in factoring is I can factor this as x plus 5i and x minus 5i, which when I find my solutions using the zero product property, that will give me -5i and +5i as solutions. A similar thing will happen on this other example, 10x plus 3i and 10x minus 3i. I. And that will give me the solutions negative 3I over 10 and positive 3I over 10. It is important that you have these examples probably side by side in your notes so that you can see the comparison between the two